In this video, we're going to talk about another example of integration by parts. So here we have the function x squared times e to the x. It definitely looks like a product of two functions. And if we follow the LIAT guidelines, then we will know that we would pick u. We have an algebraic function, a power function, which is an algebraic function, and e to the x, an exponential function, right? So according to those guidelines, you would pick x squared, the algebraic function, to be your u, and then that sort of forces the rest of it, right, to your dv to be the rest of it, which is e to the x dx. So again, if we just stop here and just double check ourselves, hey, if we multiply u and dv together, do we get all of this stuff in here? And the answer is yes. X squared times e to the x dx, that's the entire integral up here. So that looks good. Next, we will calculate our du and v, right? We calculate du by taking the derivative. So the derivative of u would be 1. The derivative of x squared will be 2x. And then we calculate v by taking the antiderivative. So the antiderivative of v dv will be v, or 1 dv will be v, and the antiderivative of e to the x is itself, right? It's e to the x. And so there we follow the formula for integration by parts, right? Our u will be x squared times that by v, we get x squared e to the x. Subtract off the integral of v, which is e to the x, and then du, which is 2x e to the x. And I just kind of wrote this in the more standard way to write that. Okay, and so now what we need to do is to finish off this integral right here. All right, I will go ahead and pull this 2 out using the constant multiple rule there, right? That says the indefinite integral of a constant times a function is just rewriting that constant, right, or pulling it out, kind of looks like, times the integral of the function itself. And now, right, how do I compute the integral of x e to the x? Well, if that was pretty much the first example that we did back when we introduced integration by parts in that video, and so we have to use integration by parts again. So sometimes, right, with some functions, you will have to repeatedly use integration by parts in order to completely integrate the function. So we would just run through there. We're going to pitch out the old u and dv, and now just focus on this integral right here. And again, our u is going to be x, and dv is going to be e to the x. Again, it's the exact same function from the first example. Calculate du and dv. So du will be dx, right? And integrating dv, I get v equals e to the x again. E to the x is its own antiderivative there. Okay, and apply the formula for integration by parts again. All right, so looking here, right, I have this integral right here. I'm replacing that with the formula for integration by parts. So I'd still have this minus 2 on the outside, right? And on the inside, I'd have uv, which is x e to the x, minus the integral of v, which is e to the x, du, which is dx there. Okay, so again, I'm taking this bottom equation here. How did I get that? I took and replaced this integral right here with what it was equal to, right, using the integration by parts formula there. All right, so next up, I will do a little simplification. So I had this, right? And what I would do is distribute that 2 through the parentheses. So negative 2 times x e to the x will be negative 2x e to the x. And then I'm going to distribute this negative 2 times this integral right here. So negative 2 times this negative 1 will give me a positive 2 times this integral right here. All right, and now this is an easy integral to compute, right? The integral of e to the x, again, is just e to the x. And so that's what it becomes. I still have this 2 e to the x here. And don't forget to add your plus c onto the end. And so that's it for this example.